The Maple Quantum Chemistry Toolbox from RDM Chem is an add-on package that essentially adds to Maple the capabilities of doing electronic structure calculations of atoms and molecules. I'm David Mazziot. I'll be one of your presenters today. After I present the first part of the talk, my colleague Jason Montgomery is going to present the second part on using the package for education. All right, the Quantum Chemistry Toolbox, or QCT. Let me give a brief introduction today. It's a modern, easy-to-use package with actually several different interfaces for accessing different aspects of the package. For example, you can access it using a worksheet interface. So quantum chemistry calculations can be directly performed within the worksheet interface. So here's an example, a screenshot of the package in action within the Maple worksheet. Also, you can use a command line interface. The command line interface allows one to perform calculations with essentially batch scheduling. So you can basically run lots of calculations at the same time in Windows, Mac OS, and also Linux. Here's an example of running initializing the quantum chemistry package within the Maple command line. We can also use a maplet interface. And the maplet interface allows one to perform calculations from within an advanced graphical applet in Maple. Okay, so let's dive in and actually see how do we use the quantum chemistry package to do innovative quantum chemistry. Well, first of all, it has some major features and advances over traditional programs for electronic structure. So for example, we can use a web molecular database to import atoms and molecules. So it's easy to import the geometries of large and small molecules from an online database of 96 million molecules. First, we set the digits in Maple to 15, and then we use the with command to load the package, the quantum chemistry package. Okay, so there are the different commands in the quantum chemistry package. Let's illustrate this by importing and plotting the bioluminescent molecule luciferin. We use the command molecular geometry, passing in the string luciferin. If we hit return here, okay, we've just retrieved the geometry as a Maple list of lists from the web. Furthermore, we can use the plot molecule command to provide a ball and stick plot of the molecule luciferin. Clicking on the plot here, we can use the plus magnifying glass to magnify or shrink or magnify the molecule. Okay, to zoom in, we can click on the rotate here, which allows us to rotate the molecule to see it from different angles. Okay, so we have that. Let's go ahead and take another molecule. We'll look at the explosive molecule RDX, import its geometry using molecular geometry. Let's go and plot that molecule as well. Okay, so here's the RDX molecule. We can rotate it to look at it from different sides. How about the preservative molecule formaldehyde that we're familiar from biology labs? Okay, we can import the molecular geometry formaldehyde using the string formaldehyde, and we can plot the molecule using the plot molecule command. Again, we can rotate the molecule to view it from different angles. Okay. All right, so now we're going to scroll down a little bit further. We can also import the skeletal structures of luciferin using the skeletal structure command in Maple. So hitting return here, voila, we have the skeletal structure of luciferin. Likewise, we can import the skeletal structure of the molecule RDX or the skeletal structure of the smaller molecule formaldehyde. Another property that's unique to the package is on-demand energies and properties. For example, the ground state energy of the luciferin molecule can be computed using just the energy command. So let's say we take energy and now we're passing in the geometry imported from before, which we saved to the Maple variable luciferin. Energy of luciferin goes ahead as we hit return here, and we'll go ahead and compute the ground state energy of luciferin using the default method. And so here we have the ground state energy. We can also calculate molecular orbital energies, passing luciferin into the MO energies command. And that gives us a list of the energies of each of the molecular orbitals of the molecule luciferin as a 106 element vector. We can also look at the occupations by using the MO occupations command. Importantly, we're not redoing the calculation each time we hit return here. Maple's actually smart enough in the package to do the calculation once and use advanced remember tables in Maple to retrieve the information upon request. For example, we can calculate or retrieve the dipole moment now for formaldehyde. We can easily plot its dipole moment. Okay, so we end up with a plot showing the direction of the dipole moment relative to the structure here of luciferin. We can kind of zoom into this as well to get a closer perspective. We can look at the charges in luciferin. And so now we have the charge on the sulfurs, on the oxygens, okay, etc. We can plot this as using the charges plot command. And this gives us a nice visualization of the charges of the molecule luciferin. If we zoom in here, the blue atoms represent the negative charges, and the red atoms represent the positive charges. And we can also hit on the rotate to rotate the molecule to see the charges from different directions. We can also compute the excited state spectra of luciferin. Okay, so here we have the molecule luciferin, we have the states, we have the energies in electron volts. We can also change the keyword show table to true to provide a fancy table for the information as well. We can also use excitation spectra plot to produce a spectra plot of the excitations. And so here we see the wavelengths of light at which absorption will occur for the molecule luciferin. Okay. Now, the package also supports calling an electronic structure method directly with the output collected in Maple tables, which are really great for doing programming on top of that. The package has standard methods like density functional theory, coupled cluster theory, to advanced theories for strong electron correlation like those based on the 2-electron reduced density matrix. So here we're going to run a variational 2-RDM calculation on formaldehyde using an active space of 4 electrons and 4 orbitals. And this illustrates the Maple table that comes out that contains lots of information from the molecular orbital coefficients to the correlation energy, the atomic populations, the 1-electron reduced density matrix, etc. So all the information is returned in a programmatically accessible table. For example, we can calculate or retrieve the total energy by taking our variable V2RDM and extracting E total, or for example, the dipole moment. We can use density plot 3D, for example, to give us a 3-dimensional plot of the molecule formaldehyde. Here we're using the variational 2-RDM method to do that. We pass in the geometry of formaldehyde and the output data table V2RDM. So that's all that's needed to generate the density plot 3D. Okay, so out comes a 3-dimensional plot of the density, the total density of formaldehyde. Likewise, we can plot a specific orbital. So for example, if we want the 8th orbital of formaldehyde, we can hit return here, and now we'll go ahead and calculate the density specific to that molecular orbital. Okay, so here's our molecular orbital. We can click on this. Again, we can rotate. We can also zoom into this to get a closer perspective of the molecular orbital. Okay, so now we're going to talk briefly about the importance of the fact that this package is in the context of Maple. And Maple has 5,000 commands for mathematics and science. And so the Maple language and the Maple commands provides a really rich background for using the commands in the package to do all sorts of other calculations that are essentially impossible with traditional approaches to quantum chemistry packages. So to illustrate the power of the Maple programming language in combination with the Toolbox, we compute the equilibrium bond length of carbon monoxide. So first we use the Chebyshev command to retrieve the 6th order Chebyshev polynomial. We're going to expand that in powers of x. Then we're going to find the roots using the fsolve Maple command. We can turn that into a list with another command. Now we're going to use the map command to basically map the roots here of the Chebyshev polynomial to the bond length region. Okay, so it's a linear map now giving us the bond distances that we care about. We can define a list of molecular geometries with each geometry corresponding to one of the bond lengths, again using the map command and mapping the input bond length to the structure of the molecule that we need as input for the quantum chemistry package. So now we have a list of molecules at the different bond lengths. We can again use the map command to map the energy command from the quantum chemistry package onto each molecule. As we hit return here, this command will generate the energy of each of the molecules. Now with this at hand, we can use the interpolation command to do polynomial interpolation over the bonds and the energies as a function of R. So this gives us a fifth order polynomial in the bond length R as a variable. We can use our plot command in Maple to generate a nice one-dimensional plot of the energy as a function of the bond length. Likewise, we can use differentiation of the polynomial, set it to 0 to find the minimum. Okay, so that equation, by solving that using fsolve, we find that the equilibrium or minimal energy bond length corresponds to 1.146 angstroms. This also illustrates the power of using other Maple packages. For example, using the Maple units package, we can append the unit angstroms to the computed bond distance. We can then convert the distance to any other unit. For example, picometers, we can use the convert command to picometers, or we should have actually had nanometers here, so we can change that very quickly, comma, nanometers. We can convert to centimeters, or we can convert to meters, or to something even quite a little bit unusual for science, furlongs. Okay, so here we actually have it in terms of furlongs used in horse racing. Research and publications. The quantum chemistry toolbox has been used in the computations and visualizations of a variety of published papers. For example, the stacking of inorganic molecules or organometallic molecules has been investigated, and by changing the geometry of the molecules, the degree of interaction can be carefully tuned for a variety of important applications. Finally, the quantum chemistry toolbox has, unlike a lot of other packages for quantum chemistry, has a built-in curricula for chemistry and physics courses. And so course materials available for general chemistry, physical chemistry, computational chemistry, and graduate level quantum chemistry. So with that, I'm going to turn it over to Jason Montgomery, my colleague, to tell us more about using the quantum chemistry package in Maple for learning chemistry.
Hello everyone, my name is Jason Montgomery. I'm faculty at Florida Southern College, where I mainly teach general chemistry and physical chemistry. So as David pointed out in his talk, the advantage of the quantum chemistry toolbox is that it combines molecular modeling with Maple's computational and visualization functionality, all in the same graphical interface. So for my portion of the talk, I want to look at how the quantum chemistry toolbox can be leveraged in the chemistry classroom. Contained in the quantum chemistry toolbox are a set of lessons which can be viewed individually, but they're also compiled into a set of curriculum pages. For example, the general chemistry curriculum page contains a range of topics from the structure of atoms and molecules to thermodynamics to quantum chemistry. I want to begin by looking at the particle in a box. Each lesson contains a quick overview that reviews prior knowledge and learning objectives. In this particular lesson, students will explore the allowed energy levels and wave functions for a 1D particle in a box to show how, as system size increases, the quantum behavior will approach the classical limit. We begin by looking at the discrete energy levels, and for simplicity, we use atomic units. Using Maple's with_plot command, students can consider a box of length 1 atomic unit and a mass of 1 atomic unit, corresponding to the mass of an electron. As with many of the lessons, the required Maple code is already provided, but instructors can modify any of the lessons to fit the coding level of their students. Here, students see the discrete energy levels for energies less than 10 atomic units. So students see the spacing between energy levels increases for increasing energy, a very non-classical behavior. They are then asked to consider larger particles or boxes. Here we can change the length of the box to 10 atomic units and replot the energies, seeing the allowed energy levels becoming more like a classical continuum. Discussion questions are typically embedded to emphasize the learning objective. Students are now asked to explore the wave function solutions, in particular the probability distribution. This time, using Maple's explore command, students can plot the probability distribution as a function of x and toggle n. For n equal to 1, we see the probability for finding the particle as a maximum in the center of the box. This is actually a very non-classical behavior. But as we increase n, the probability distribution goes to a constant everywhere in the box, a more classical behavior and again depicting the Bohr correspondence principle. Students can now use the quantum chemistry toolbox to make an interesting connection between the 1D particle in a box and a chain of 5 hydrogen atoms. They initialize the package and define the chain of atoms as a list of lists. Again, the code is already provided. Using the plot molecule command, students can visualize the chain of hydrogen atoms. This is their 1D particle in a box. The narrative now connects the idea of molecular orbitals to the probability distribution for a particle. Using the Hartree-Fock command, students calculate the ground state energy, as well as the energies of molecular orbitals. The table of molecular orbital coefficients includes the necessary data to plot the molecular orbitals as using the density plot 3D command. I've copied the explore plot here to remind the student of what the lowest energy MO should look like, having a max in the center of the box. We indeed see a maximum in the center of the hydrogen chain. If we toggle to n equal to 2, we see a node in the center of the box. Plotting the next molecular orbital, we see a node in the center of the hydrogen chain. Finally, one more example is if we set n equal to 3, we should see 2 nodes in the molecular orbital. And again, the next molecular orbital indeed has the expected 2 nodes. At this point, students should have a better understanding of how the simple 1D particle in a box model can actually connect to real molecules. Very briefly, another lesson from the physical chemistry curriculum page is the geometry optimization and normal modes lesson, in which students calculate the optimum geometry and the vibrational frequencies of hypochlorous acid, a primary disinfection agent in chlorine solutions. As an example of how instructors or students may modify the imported worksheet, I'm choosing to use the density functional method and the 631G basis for this activity. Students can start with an initial guess for the geometry of HOCl. We can define the molecule and plot our initial guess for what the geometry might be. We can calculate the energy of the starting guess, the energy given here in the variable data not. Students can then optimize the geometry using the geometry optimization function. We can calculate the difference in the energies to see that the minimum energy geometry is indeed 44 kilocalories per mole smaller than the initial guess, about half the energy of a chemical bond. The bond angles and bond distances function can be used to extract the new geometry parameters. Finally, students can calculate the vibrational frequencies, or normal modes, of their optimum structure. The vibrational mode animation function can be used to visualize the vibrations. We see the first normal mode corresponds to an OH stretch. The second normal mode corresponds to a bending motion. And the third normal mode corresponds to the OCl stretch. Students can compare the experimental values provided to their calculated frequencies and re-execute the worksheet with a larger basis set or more sophisticated methods to attempt to get closer to the experimental values. Finally, it's straightforward to change the molecule. Consider sulfur dioxide, a triatomic molecule typically encountered in the physical chemistry laboratory. So we see it's straightforward to change the molecule and to re-execute the worksheet to calculate any molecule that may be of interest in lecture or in lab. At this point, we hope we've demonstrated the potential impact that Maple's quantum chemistry toolbox can have not only in research but also in the chemistry classroom. We appreciate you taking the time to watch, and we look forward to answering any questions you might have.